Okay, question 20. I'm not much of a drawer here, but what they're asking you to do is the arrow is saying that's the front, and they're asking you to create an orthographic projection. So orthogonal projection of the third angle projection, which is the one that AS 1100 demands, is like opening up this box. So you need to look at, I've got videos in the drawing resources on Exchange telling you the difference between first angle and third angle projection. So what I've done is, first of all, I think about what this would look like from the front, and I look at these measurements. So we've got 35 plus 30 plus 35. We've got 100 mils across the bottom. So we know we've got 100 mils across the bottom. So I started down here, the front view. I measured 10 centimeters and I made that 100. And you can see I've just projected lines down or lines up to give myself a bit of guidance. So I started with my front view on the bottom right hand corner. And then I also looked at this height here, which was 50, which is what how I measured that there, 50. And then I just used these measurements to work out this front view. Then I projected lines up, and I got an idea of what my top was going to look like. And then finally, I thought about this side here, the left side, and what it would look like. I've also made sure I put in a projection symbol for third angle projection. I put in the essential dimensions with dimension lines, which should be a little bit lighter than the outlines. And I've also labeled top, front, and left view. So I think that would be enough to get the marks required for this question. If you can think of anything that I've done wrong or you want to add to that, please let me know by email. Okay, this question here, had a little bit of trouble with it at first because I actually thought about this force acting upwards. Now we know that with a simple lever in equilibrium, that some of the moments and the sum of the forces has to be equal to zero. So what's happening here is we actually have a force acting down that's being provided by this bottle cap that we're trying to pop off the bottle. So your FA, your force A, has to be acting down, okay? Your hand is pulling up, okay? The 50 newtons is pulling up. So you've got 50 newtons creating around the pivot point. This is the other problem. You tend to think the pivot point would be point A, but of course we're pivoting on the end here. So if you pivot at the end and your load, which is where the work is happening, because work is where the load is happening, this is actually a class 2 lever. Okay, so pivot at the end and our load. So if we imagine this is a wheelbarrow and P is our wheel, this would be like having a weight sitting where A is, point A is, and the load would be, the force would be acting down. Okay, so that's why FA is acting down. And we're pulling up to lift the wheelbarrow up. So anti-clockwise direction I've said is negative and clockwise is positive. So you've got the sum of the moments, well, the moments is equal to force by distance, and the sum of the moments, when you sum them all up, they're going to be equal to 0 if it's in equilibrium. So first of all, we work out our effort arm. So it's force times distance. So we've got 50 newtons, but with a class 2 lever, we have to add up all the distances from the where the effort's applied right down to the pivot. So we've got 0.025 plus 0.06 because I've converted our millimeters into meters. They need to be converted, and I've said that that is going to be subtracted from the clockwise, which is the positive rotation, which is this FA force, and this FA force is FA times 0.025, which is the distance from FA to the pivot. So FA is rotating us in a clockwise direction, and the force of 50 newtons is anti-clockwise. And when you add the two together, we get 0. So if you solve this whole equation for FA, which is the force that they were asking for, we get a force of 170 newtons, and we can just say acting upwards. So 170 newtons. So let me know if you understand that question. If you don't, by all means, come and see me. Turning, this is just a mechanical process, a fabrication process, a cutting process. Okay, so wood is turned or could be metal or plastic even, is spun along its longitudinal axis. And this is the sort of thing they do for like table legs and chairs and balustrades to make nice shapes. And a tool is placed on this spinning material to remove material, okay, cut from it. If you don't understand that process, by all means go on Exchange. I put a whole lot of stuff about that on Exchange for you. If you can't find it, let me know. Simple machines, we did this in class. We talked about the mechanical advantage of a drive chain. They should actually have the drive and the driven labeled, because this could be either a mechanical advantage or disadvantage depending on how you actually do the maths on this and which one's the drive and which one's the driven. But I've assumed that the drive gear is the left and the driven is the right. So first thing they ask you, they say that in the comprised of two wheels, the driving wheel is A. So they actually tell you the drive wheel is A. Good. So in the question, didn't read the question well, Mr. Komanos. Drive A is A, so I've made the right assumption. Wheel B has 25 teeth and wheel A has 15 teeth. And they're saying determine the velocity ratio. So velocity ratio is equal to the number of teeth of the driven over the drive. So we say 25 over 15, we get 1 2/3. So that's our velocity ratio. Now, velocity ratio never changes, but if there's an efficiency loss, a mechanical advantage does change. So if we're going to say eta, which is our efficiency, it's equal to the mechanical advantage over the velocity ratio. So they've said the mechanical advantage is 0.85. Sorry, the efficiency is 0.85. So what we do is we just say 0.85 equals ma over our velocity ratio, which we already know, and we solve for ma, and we get 1.42. Okay, and then for C, we've got a drive chain here, and we've got a gear in the middle here. Now, I don't know if you remember what that gear is called. It's actually called an idler gear. And it doesn't matter what size that gear is, within reason, of course. If it's too small, you'll get mechanical issues. But for a reasonable size, it could be very, very large or very, very small. It will not affect the mechanical advantage of this system or the velocity ratio at all. So what it will do, is if you look at this example here, if A is turning clockwise, then B will turn anti-clockwise. So if you wanted both gears turning at the same rate with the same velocity ratio, you can throw a gear in the middle here in this gear train, and this idler gear will reverse this direction. So if this is turning clockwise, B will turn clockwise, or turn in the same direction. So it says here, the question is, state two effects. So one effect's really easy. It's just a reversing of the direction of rotation. So B becomes the same as A rather than the opposite. The other one is it increases the distance between the centers of A and B. So you can see A and B are further apart. Now you may say, oh, well, what's the point of that? Well, if you had two gears that were the same size and you had them pulling a belt, you just wanted to have more teeth engaging with the belt, you could have two big gears or three big gears, and that way you'd have the same velocity ratio but more torque, more teeth grabbing the belt. So it's just increasing the distance between centers. So you need to remember that that's two things that an idler gear does. It reverses direction and it increases the distance between the centers of the two gears. Here we're saying prove that the size of a wheel has no effect, of the idler gear has no effect on the velocity ratio. So what I did was, I said the velocity ratio of the original setup of just two gears was 1 2/3, and then I put two scenarios. One where C was 5 teeth and one where C was 10 teeth. So where C was 5 teeth, we went driven over drive, so we go 15 to 5. Sorry, 25, because B is 25. So basically what I did was I said gear B, which is 25 over the idler of 5, and then I multiplied by the idler of 5 over 15. So you get 5 times 1/3, and lo and behold, you get the same. You get the same velocity ratio. And same with this one here. When I made the idler gear 10 teeth, driven over drive, so the big gear B was 25, going on to 10, and you multiply that by the idler gear 10 over the wheel A, which is 15, and you will see that that also comes out to 5/3, which is 1 2/3. So if you don't understand that, by all means come and see me, but you really need to do some gear problems to see that. But if you ever get a really complex problem with like 20 gears, and they're all in a chain, and it's not a compound chain, it's just a simple chain, you just have to know the last number of teeth, the driven gear, and the first gear, the drive, and you can work out the velocity ratio, provided the velocity ratio will stay the same. Mechanical advantage might differ because of friction in the system, but velocity ratio, if it's a lossless system, the velocity ratio equals the mechanical advantage. But all you need to know is the first and the last gear to work out velocity ratio for a string of gears. Okay, last question is this type of block and tackle, and like I was saying, you can count the number of, in this instance here, you could count the number of pulleys, 1, 2, 3, 4, 5, you get a velocity ratio of 5. But the reason why I was saying you should count the ropes is because you could have a pulley down here on the ground that's just so that you can pull up on it rather than down, and it would not change the velocity ratio. So it's better just to look at which block is fixed and which block is hanging, and look for that center area and count the ropes. So you've got 1, 2, 3, and I've labeled them here. 1, 2, 3, 4, 5. That gives us a velocity ratio. Now the question is asking, the lifting tackle below contains 3 pulleys in its upper block and 2 in its lower block, and they've given you an efficiency and a load effort, and they're asking you determine the load that can be raised with that 100 newtons of effort. So what I've done is I've said mechanical advantage is equal to 0.785 times 5. Okay. Now how did I get that? I got that from the fact that efficiency is equal to MA over VR, okay, which we talked about in the last question. So I probably should have given you that information there, but it's MA over VR equals 0.785. So when you make MA the subject of the equation, you end up with a mechanical advantage of 3.925. So for 100 newtons of effort, load is equal to 3.925, which is mechanical advantage by 100. Okay, so we end up with 100 newtons of force here can lift 392.5 newtons, provide that much load force, and you divide by 10 to find out what weight that is. So basically 10 kilos hanging off this rope where the effort is would be able to lift 39.25 kilos down here. Anyway, hope that's helpful. Have a look at the solutions, work through them. If you have any questions or any problems, please come and see me before it's too late.